In this video, we're going to continue, yet again, hypothesis testing. This time, we are on our fourth step, calculate the test statistic. So we're going to get the kind of nitty-gritty out of the way right at the top. This is how you calculate the test statistic. All right, so the z-stat, or you could just call it z, z-stat equals x bar, so our sample mean, minus c, that's our arbitrary constant, divided by sigma, the population standard deviation, although normally we're not going to have that, so we could also use s here, right, the sample standard deviation, and then we're going to divide by the square root of the sample size, or n. All right, so that is the way we're going to calculate that. Now, what this is, or what the test statistic is, what its purposes is, that's not how you say that, but let's carry on. All right, so the purpose of it, all right, again, we're going to go back to our analogy of the hypothesis testing as a criminal court case. So if we are looking at this test statistic, this is our evidence, right? So that's essentially what it is. It's our evidence based on sample data about the characteristics of this population mean. All right, if our evidence is strong enough, then we will reject the null hypothesis and conclude that the alternative is true. If it's not strong enough, we will fail to reject the null hypothesis. All right, so it is our evidence. It is also a standardization of the sample mean. So if we think back to chapter 8, we were looking at standardizing our sample mean, right? We went through the whole process of talking about how it is a random variable, so on and so forth. And we came up with this formula to standardize it, right? So our random variable, x bar, minus its mean, which is the population mean, right? So again, that whole unbiasedness aspect of the sample mean, divided by the standard error, right? Or the standard deviation, which in this case, for the sample mean, is sigma divided by the square root of n. Now, this should look familiar because it looks very similar to something that we had written up on the board just a second ago, which is our z-stat. All right, so having them side by side, we can see what the difference is, right? Instead of mu, we have c. All right, so why is that? It's easiest to see with a two-tailed test, but let's put up the generic hypotheses for a two-tailed test. So for our two-tailed test, right, our null hypothesis is that mu equals c, and our alternative is that mu does not equal c. So what we're doing when we are calculating and also, actually before I say that, also note that all of the or equal to, all right, equal or equal to inequality or equality terms in our hypotheses, those are always in the null hypothesis, right? For the two-tailed, it's mu equals c. For right-tailed, it's mu less than or equal to c. For left-tailed, it's mu greater than or equal to c. All right, so the null hypothesis is saying mu equals c. So when we calculate our test statistic, what we're really doing is we are standardizing the null hypothesis under the assumption that the null I think I said that slightly wrong. When we are calculating the test statistic, I think I said null hypothesis there for the first time. When we are calculating the test statistic, right, we are calculating it, what we are calculating is a standardized version of the sample mean under the assumption that the null hypothesis is true. All right, so why does this matter? All right, the reason this matters is because we're going to compare that test statistic to our critical value, right, to our rejection regions. So since we're using a two-tailed test, let's just go ahead and pop some rejection regions in there. All right, also remember that with a two-tailed test, we have two rejection regions. All right, so this is really what all of hypothesis testing hangs on. All right, so let's say that the null hypothesis is true in this case, all right? That mu does equal C, all right? If that is true, right, then we would also expect the sample mean to be close to C, right? Because the sample mean is used to estimate the population mean. If the population mean is C, then we would expect X bar to be close to C, right? If the null hypothesis is true. All right, so if that's the case, right, then when we get up here in our numerator and we subtract these two from each other, if the null hypothesis is true, we should get a value close to 0, right? Or close enough to 0 that when we divide by the standard error, that our test statistic is close to 0. All right, if it's close to 0, all right, if it's within this white area of our distribution, all right, then we're essentially saying, well, that looks like it's close enough to C, right? We can't really say it's not C, all right? We can't really state anything strong about this, right? But if mu does not equal C, right? If the alternative is true, right? Then the difference between X bar and our arbitrary constant is going to be larger, right? That's at least what we would expect, right? We would expect this to be closer, all right, X bar to be closer to mu, right, than to C, right, if C does not equal mu, right? So this numerator will be bigger, right, making the whole term bigger, right, making it more likely that we fall into one of these rejection regions, which is how we're going to state our conclusion, all right, or make our conclusion. All right, I find all of this stuff very fascinating. If you're not really getting it, that's okay. The main thing is this formula. All right, knowing how to use this formula, all right, plugging in the different values, all right, and then using the output for the next step that we're about to cover. All right, but we'll go ahead and leave that there. Again, the test statistic is the evidence that we're presenting, right, based off of our sample data. This is the only place sample data is going to come into play. All right, it is a standardization of the sample mean under the assumption that the null hypothesis is true. All right, so let's move on to our fifth and final step. All right, so our fifth and final step is to reach and state the conclusion. All right, so when we are doing this, first, just to reiterate, there are two outcomes when we do hypothesis testing. All right, we either reject the null hypothesis or we fail to reject the null hypothesis. Right, we're going to talk a little bit more about that in just a second, but those are our two outcomes. All right, we're going to state all the conclusion criteria in terms of rejecting the null hypothesis, and then you can just work from just whatever the opposite is. That's when we fail to reject. All right, so let's start with what is probably the more difficult one to write down. All right, so the easiest way, I mean, none of the ways are that difficult, but one way that we can do this is we can use our rejection regions, right? So if we're looking at a two-tailed test, and we've got our critical values, then all right, so now if we've got this two-tailed test, all right, any critical value that falls into the rejection region, or in either rejection regions, right, you're going to reject the null hypothesis, right? So these red areas in the tails, those are the rejection regions. If your test statistic falls into one of these regions, you reject the null hypothesis. So we've also got that mapped out down here. So the green area, you reject the null hypothesis. If your test statistic falls in between those critical values, right, into this blue area, then we would fail to reject the null hypothesis. I'll leave that up for just a little bit longer. All right. Right, mathematically, the way that we might write it so if the absolute value of the test statistic is greater than the absolute value of the critical value, then reject the null hypothesis. All right, it's not a great way of writing it, and this isn't exactly how I would expect you guys to do this in your heads. Bottom line is that if your test statistic, the thing you actually calculated, if that's negative, then you want to look at the negative critical value, right? And if it's less than that negative critical value, you'll reject the null hypothesis. If you have a positive test statistic, you want to compare it to the positive critical value. If it's greater than that, then you want to reject the null hypothesis, right? So another way of saying it is that if your critical value, if your test statistic is more extreme than your critical value, reject the null hypothesis. If it falls between them, right, then you're going to fail to reject. All right, so that one's kind of the weirdest one to just write out. The other two are very much simpler. So let's look at those. So let's look at our one-tailed. So let's start with the right-tailed test. So when we're doing a right-tailed test, if the z-stat is greater than your critical value, then you're going to reject the null hypothesis. Might not have given myself enough room over here. That's all right. All right, so again, remember, all right, another way we can look at it, if we're looking at it graphically, for a right tail test, we should have that rejection region in the right tail. Rejection region. If your test statistic falls into that rejection region, you will reject the null hypothesis. If it falls outside of that rejection region, you're going to fail to reject. All right, so we could also say, so red is the rejection region. All right, and this kind of wonky blue area is the fail to reject. All right, and last but not least, we have our left-tailed test. Again, similar to our right-tailed test, very simple. If our z-stat is less than our critical value, then we will reject the null hypothesis. All right, so again, all right, when we are dealing with a left-tailed test, we should have a negative critical value. We should also have a negative test statistic. If you have a positive one, then you've definitely failed to reject, because there's no way it would. Anyways, that's not important. All right, most of the time you're gonna have a negative test statistic as well. All right, so if your test statistic is less than that critical value, it's going to fall into this rejection region over here in the left tail. If it is greater than that critical value, it's going to fall into this blue region, which is where we would fail to reject. All right, and that is essentially it as far as those conclusions go in that criteria, that conclusion criteria. Right. The last thing that I want to say about these conclusions is that there is a difference between the two in the way we interpret them. All right, so a lot of the time in here, I'm just going to write reject HO. All right, but really what we need to be saying is reject HO, conclude that H1 is true. All right, so by rejecting the null hypothesis, we're concluding that the alternative is true. That's our conclusion. That's not saying that we were right. Obviously, due to the presence of type 1 and type 2 errors, that has to be the case, that we can be wrong. So when we reject the null hypothesis, we're going to conclude the alternative is true. If you're given a problem and it has kind of a scenario with it, you need to state that, you need to, instead of saying, let me back that up. Instead of saying conclude H1 is true, whatever it means for H1 to be true, that's what you need to say, all right? That's what your conclusion needs to be. You need to include that, conclude, you know, the population mean for, I don't know, whatever it is, right? equals this or does not equal this or is greater than that, whatever the alternative hypothesis is saying. We'll work more with that once we get into the video where we have examples. All right. On the other hand is when we fail to reject. All right, when you fail to reject, that's all you say. All right, we do not make conclusions based on failures to reject. Right, we can, in the real world, you would probably make some inferences and you would probably make some decisions based off of a test where you failed to reject. But technically, it's not concluding anything. It's not proving anything. We're just failing to reject. Right. So once again, to bring back our criminal case analogy, just because someone is found not guilty, right? There's a difference between not guilty and innocent, right? So just because someone's found not guilty in a court of law does not mean that they didn't do it. It just means that we don't have enough evidence to prove that they did it, right? We've got it's not the exact same, but it's similar in this scenario, right? Again, we're never going to be able to prove an absolute, right? Fail to reject is a much weaker statement than reject the null, conclude H1 is true. That's why what we want to prove, right, should be the alternative hypothesis, right? And what we, either don't care as much about proving / can't prove, that's why we want to put those in the null hypothesis, right? Because the strongest statement we can say about the null hypothesis is that we failed to reject it, all right? So again, reject HO, you need to have a conclusion, and if you're given a scenario with any amount of details, you need to tailor that conclusion to those details, right? If you fail to reject, that's it. You can just say we failed to reject the null hypothesis because you can't make any conclusions off of that. All right, so before we go, just want to quickly put up the steps for hypothesis testing once more. All right, so we need to state our hypotheses. That's the first step, all right? So we need to, we need to know whether we're doing a right-tailed test, a left-tailed test, or a two-tailed test. We need to get our arbitrary constant set, and we need to know how to set up our null and alternative hypotheses correctly. All right, second step, specify the significance level, or alpha. Again, most of the time this step is going to be done for you. I'm going to specify the significance level. Either I'm going to tell you to do it at some certain confidence level or a significance level, or I might tell you to do it with an alpha of something, right? All of those things are tied together. They're all going to tell you that significance level, right? You can get alpha from any of those, right? Also remember, alpha is the probability of making a type 1 error. And we want to minimize that as much as possible. And we're going to base these off of those three commonly used confidence levels, right? Or significance levels. 1%, 5%, 10%, or for the confidence levels, 99, 95, 90. All right, third step is that we need to determine our critical value. All right, CV, that's critical value. We need to determine our critical value, so we need to know, once again, whether we're doing a one-tailed or a two-tailed, right? So we know whether we're dividing alpha by 2 or not. So we divide alpha by 2 for our confidence intervals and our two-tailed test. We leave alpha by itself for our one-tailed test. All right, we also need to remember to make the critical value negative if we're doing a left-tailed test, and remember that we have 2 critical values if we're doing a two-tailed test. Our fourth step is to calculate calculate the test statistics. So again, this is our evidence that we are presenting to the jury, all right? This is based off of our sample data. This is the only thing we're actually going to calculate. And it is a standardization of the sample mean under the assumption that the the null hypothesis is true. All right, and then fifth, we need to state our conclusion. All right, so those are the 5 steps of hypothesis testing. If we go through them kind of categorically, right, then it can make it easier for us to know what we need to do. All right, we're gonna see these more in action in the next video when we start looking at some examples. All right, but for now, we are now done with all of the concepts of hypothesis testing. All right, the only thing we have left to do is to put it into practice with some examples. All right, that's coming in the next video, and I will see you then.